Hello everyone. Today I am going to describe our Matlab project, which is simulation and analysis of linear system responses using Matlab. My name is Shishir Kumar Sarkar, student ID 23230605, and my partner is Shourapal, and student ID is 2306086. Let's start with code. As you can see, this is a code browser window of Matlab. At first, you will see the matlab.apps.app base, the base class that app designer uses for all apps. This gives our app built-in functionality like component management, callbacks, and UI rendering. Then we will talk about the properties section here. These blocks declares every single UI component that exists in the app. Each correspond to a visual elements, button, say, labels, edit fields, axes, tabs, and images. This is declared public because it means these components can be accessed from the outside the class if needed. App designer generates this automatically. In We will just talk about the base core function of our app, like startup function, which initializes the all value all values in the app. Then I will talk about FCF, which is from cutoff frequency. Here we determine a filter using cutoff frequency. Like if you select a low pass low pass filter using RC circuit, just select it, and the and the app will determine the circuit and give you magnitude plot, phase plot, data and error, and schematic values. Okay, so here we used f for taking points. We take 1 million points in the logarithmic region that give the smoother graph, and we can observe it easily. Then we determine the value of tau, which is 1 by 2 by fc, and then we determine the transfer function, which is the basic transfer function, standard function for a low pass RC filter. Then the magnitude, if magnitude phase plot are checked, boxes are checked, then then the app will show the plots. Okay, in the schematic section, um, we used a default value of R, which is 1000 ohm or 1 kilo ohm. Using this, we know a theory from 1 to that 1 to means level 1 term 2, that um, FC is equals to 1 by 2 pi RC for low pass RC filters. From that, we can determine the value of C. So if you want to change the value of R, then just simply give an input and the app will dynamically change the value of C. Onto the In the next, we will talk about the data and errors section. Here the main theory is our uh, RMS formula. So here we determine the RMS error. Then what is here, um, what we compare to it? Mainly we compare it with ideal value, and we compare it with the ideal value, because for low pass filter, the output value is 1 less than cutoff frequency, and the output value is 0 greater than cutoff frequency. But in the real cases, it is not 1 or 0. So we determine the difference. Then we get a sum of the errors and squared it, then divided it by the number of points, which is L. L is equals to length of f function of f, and f is 1 million points in the log space. From this we determine the error. For every filter we did the same thing, just the theory, just the formulas are different for band pass or band stop filter. So in the band pass and band stop section, we take input lower cutoff frequency and higher cutoff frequency. Then we determine f naught or resonant frequency. Then we determine the bandwidth. From that we build the transfer function, and then same as before, we plotted the magnitude phase plot, schematic window. Then the data and error section. Here we use temp1 and temp2 variables. Then for to determine the ideal values, because in this case for us in the certain area the value is output value is 1, and out of that the output value is 0. Okay, now on to the next section, we what which is FTF, or from transfer functions. Here we take this section mostly done by the library function like step, bot, etc. So here we take input from the user our numerator and denominator and numerator. From that we build the transfer function, which is h is equals to tf num1 and tn1. So here tf is the built-in function of Matlab. Then we plotted magnitude plot and phase plot for both plots, and in the next section we determine response for arbitrary function. We take input as a string from the user and convert it into function like using a string to function. uh, then we use linear simulation, which is also a built-in function of the Matlab. Same as before, we determine the responses like magnitude or a phase. Then we determine the step response. Then we determine the step response using xt is equals to xt, and transfer it into the frequency domain, which is 1 by s, then get an output of y, which is yt. Okay, let's head to the RLC transfer function section, where you just give the value of RLC of a circuit, and the app will show the um, responses. So here we used here you can see this is for RLC low pass. So the basic transfer function for this is in the numerator it will be R, and in the denominator it will be RLC s square plus ls plus R, which will what will that will be shown in the test case section. Okay, this is the test case section of our video. Here we take a question from a book, that hs is equals to 200s by s square plus 12s plus 20. It says to show the board diagram. So the answer from the book is like that. Then we give input in our app. So we first have to select the form transfer function, then board plot section, then we have to enter the value of numerator and the denominator. So when we are giving input numerator, we have to give input like 200 and 0, because here the coefficient of s is 200 and here the constant value is 0. But if we just enter 200, then it will work like a constant. So we have to cautious about the input. Then when you click on the board plot, the board plot is shown here, the magnitude plot and a phase plot. Then so you can see that our board diagram and the answer from the book is quite equal. So we can say that our program is running perfectly. Okay, in the test case 2, it's also question from the book, which is hs equals to 12 by s square plus 3s plus 12. So the step response, this is the answer from the book, which is the step response of this function. Now we have to select the step response, and we have to enter the numerator and denominator. So here you can see that we give only 12 in the numerator. Okay, then this is our step response. So you can see that this is quite equal to the answer from the book.